In October 2017, something entered our solar system from interstellar space, and the math didn't add up. Not even close. Scientists ran the numbers again. Then again. The trajectory was impossible for any comet, any asteroid, any object that had ever been catalogued in the history of human astronomy. What they found next was kept out of headlines for months. By the end of this, you'll understand exactly what that object was, why its behavior broke every model we had, and why the gravitational anomaly that civilian observatories detected in 2017 still doesn't have a fully accepted explanation. This isn't a conspiracy. This is physics, behaving in ways it was never supposed to. Picture our solar system as a quiet pond. Planets orbiting in predictable ellipses. Comets looping in from the outer edges on trajectories we can calculate centuries in advance. For all of recorded history, everything in this pond obeyed the same rules. Then something skipped across the water from the outside. On October 19, 2017, the Pan-STARRS telescope in Hawaii picked up a faint, fast-moving point of light. At first, astronomers assumed it was a standard near-Earth object, the kind they log hundreds of times a year. But within 48 hours, the orbital data came back, and the room went quiet. The object's trajectory was hyperbolic. Not slightly hyperbolic. Dramatically, undeniably hyperbolic, meaning it had not originated inside our solar system. It had come from somewhere else entirely. This was the first interstellar object ever confirmed in human history. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. But here's where it stops being a routine discovery. Every interstellar object that theorists had ever modeled would look like a comet, an icy body that, when heated by the sun, releases gas and dust in a visible tail called a coma. Oumuamua showed nothing. No coma. No tail. No outgassing signature whatsoever. Astronomers pointed every available instrument at it. The object was silent. And then it accelerated. Here's what you need to understand about orbital mechanics. Once an object enters a gravitational field like the Sun's, its speed and trajectory are completely determined by gravity alone. We can predict it. We've been predicting it since Newton. There are no surprises. Oumuamua was a surprise. As it swung around the Sun and headed back out into interstellar space, it accelerated beyond what gravity could explain. Scientists call this non-gravitational acceleration, a polite way of saying, something pushed it, and we don't know what. The leading explanation for this kind of push in any other object would be outgassing. When a comet heats up, the venting gas acts like a thruster. Simple physics. But Oumuamua had no gas. No ice. No detectable outgassing of any kind. The force was real. The source was invisible. And this is exactly when civilian observatories started lighting up. Independent astronomers across Europe, South America, and Australia began logging gravitational perturbations in the surrounding region, tiny but measurable deviations in the expected positions of nearby small bodies. Not caused by any known planet. Not caused by the Sun. The anomalies radiated outward from Oumuamua's trajectory like ripples, from something massive that wasn't there. The data was peer-reviewed. Cross-referenced. Confirmed by 3 separate university teams. And then, for nearly 8 months, it was largely absent from mainstream science coverage. But before we get to what researchers now believe actually caused those anomalies, you need to understand something even stranger about the object's shape. Most space rocks are lumpy spheres. Gravity pulls matter into roughly rounded shapes over millions of years. Even extreme outliers, elongated asteroids, tumbling comets, fall within a predictable range of dimensional ratios. Oumuamua's ratio was 10:1. 10 times longer than it was wide. An object shaped less like a rock and more like a needle. Or a shard. Or, as one Harvard astrophysicist publicly suggested in a peer-reviewed paper, a sail. Dr. Avi Loeb, chair of Harvard's astronomy department, published his analysis arguing that Oumuamua's dimensions, its reflectivity, and its non-gravitational acceleration were all consistent with a single explanation: a thin, flat object being pushed by solar radiation pressure. Like a light sail. A technology, theoretically, that a sufficiently advanced civilization could use to travel between stars. Loeb was not speaking at a fringe conference. He was publishing in peer-reviewed journals. He was specific. He was careful. And the response from the scientific community was uncomfortable silence, followed by aggressive dismissal. But the math didn't go away. Here is what the evidence actually shows, when you lay it all out in sequence. An object arrives from outside the solar system on a trajectory that suggests it was not gravitationally bound to any known star system. It exhibits no cometary behavior despite models predicting it should. It accelerates away from the Sun without any detectable propellant. It has a shape found nowhere else in catalogued solar system objects. And it produces measurable gravitational anomalies that propagate outward along its path. In 2023, a peer-reviewed study from researchers at Penn State proposed a new model that Oumuamua may have been a fragment of a nitrogen ice planet sheared off by a collision in another star system billions of years ago. The nitrogen ice would sublimate invisibly, providing the thrust with no visible outgassing signature. It's a brilliant explanation. It's also exactly the kind of explanation that requires a process, a nitrogen-rich planet being catastrophically destroyed, that has never been directly observed and would need to happen at a rate thousands of times higher than current models allow to produce even one Oumuamua-type object reaching us. In other words, the conventional explanation requires its own set of extraordinary assumptions. And the gravitational anomalies logged by civilian observatories? The official position remains that they were measurement error. All of them. Across 3 continents. Simultaneously. You can decide what to do with that. In 2019, a second interstellar object was confirmed. Borisov. Unlike Oumuamua, it behaved exactly as expected, a normal interstellar comet, coma and all. Which is scientifically significant, because it proves we can identify a normal interstellar object, and Oumuamua was not one. The Vera C. Rubin Observatory in Chile, coming fully online in 2025, is designed to survey the entire visible sky every 3 nights. The expectation is that we will detect dozens of interstellar objects in the coming decade. If Oumuamua's characteristics appear again, the shape, the silent acceleration, the anomalous trajectory, the conversation changes. Permanently. We are, for the first time in human history, building instruments sensitive enough to catch what passes through our cosmic neighborhood. Whatever Oumuamua was, natural freak, alien artifact, or something we don't have a name for yet, the universe just sent us a preview. And it is almost certainly not the last one. The question is whether we'll be ready to accept the answer. Oumuamua came and went in weeks. By the time the world was paying attention, it was already gone, already past Jupiter, already leaving the solar system forever. We'll never study it up close. We'll never get a second look. What we're left with is data that doesn't fully fit any model, and a universe that just reminded us how little of it we actually understand. If this broke your brain a little, subscribe. We drop one of these every week. Next week, the star that shouldn't exist. It's older than the universe itself, and astronomers have been quietly arguing about it for 30 years.